Can everyone see that?
Yes.
Yes. Yes.
All right, so good afternoon and thanks for joining us today for this advisory board webinar. Today we're going to discuss some of the uses of biochar for dairy manure management and how it might be able to be used to enhance environmental sustainability. This research is funded by USDA-NRCS and USDA NLGCA. My name is Jennifer Spencer, and I'm an Extension and Research Dairy Specialist with Texas A&M AgriLife. So before we begin, I just want to ask you all to mute your mic. And if you have any questions, please type them into the comment box, and then I'll ask those to the speaker at the end of their presentations. And this webinar will be recorded and then posted on Texas Dairy Matters YouTube channel. And so if you want to rewatch the webinar, you are more than welcome to. And lastly, at the end of the webinar, there's going to be a survey link and QR code. And if you wouldn't mind taking a few minutes to fill out those surveys, it would really help us know what you think and how we're doing and how we can improve. So we're going to go ahead and start with our presentations here. Our first presenter is Dr. Khan. Dr. Khan is an associate professor with Texas A&M AgriLife Research. So Dr. Khan, whenever you're ready, feel free to go ahead and share your screen.
All right. Okay, thank you. Let me share the screen. Okay.
There we go.
Yeah, just hold on. Yeah. So everyone can see the slide?
Yep.
Hello? Yeah, can you hear me?
Yes.
Okay, so everyone can see my slide, right? I really like to present of the result and progress of two projects. One is the USDA non-land grant, capacity grant, and the other is actually NLGCA grant. So today, I'm going to briefly introduce these two projects, basically a goal and objective and current progress briefly. And also I will add some of the data from my side. And then also the following my talk, Dr. Brady and Muir will present about plant and microbiome on the different biochar condition. So my talk and focus on biocarbon, which is biochar for enhancing the agriculture and environmental sustainability. So
I'm sorry to interrupt, Eunsung. We can see your next slide and your notes as well. I don't know if you want to go to the full screen display.
Oh, sorry. Let me. Okay, let me. Okay. This is not the one. Okay, sorry. I don't know. So is it okay right now? You can see full screen.
It's the same. We still see next slide and notes, and I don't know if that's a Zoom specific thing going on there or what.
Yeah, I don't know. If it's not bother you, maybe I can just go ahead.
Sure, okay. Go for it.
Yeah. So I think the first one is the biochar. So the biochar is charcoal-like material from different waste. So as you can see, we have a different feedstock using dairy manure and grass and crop residue, wood, and biosolid. And these waste can be converted into biochar using the thermal process, which is pyrolysis. Usually we heat up 300 to 800 degrees Celsius under actual limiting condition. And in this condition, there was just a little greenhouse gas generation, mostly syngas and biochar, bio-oil generate. And then as you can see, the feedstock is converted to black charcoal, which is biochar. And so biochar can be applied for a broad range of process. And today, probably I only cover a couple of process, but essentially my research program are looking at the broad application as listed in this slide. So number one is most common application of biochar is for agriculture application. So as you know, biochar can be a slow release biofertilizer and then making soil more fertile and then enhancing soil health and then enhance water quality in the soil and field. And also, when we use biochar for the wastewater and water treatment, we can remove emerging contaminant in water using the biochar. Also, we can remove the microbial pathogen and virus using special type of biochar. And then also when we apply biochar to the contaminated site and soil, we can see actually remediation of soil and water and greenhouse gas from contaminated site. And then some of the biochar can recover nutrient and valuable compound from the wastewater. From my current study, I recover phosphorus fertilizer from biochar. Of course, one of the potential application is use biochar to recover precious metal and more importantly, rare earth element, which is an important component for semiconductor industry. And also biochar can be used for energy production and also battery. And the first project I'd like to talk about today is the USDA NIPA funded project. The title is Research Capacity Building for Enhancing Environmental Sustainability at Dairy Farm through Biochar Technology. So as it is, using biochar technology, how to enhance environmental sustainability at dairy farm. And the duration was actually 2 years, but we apply 1 year no cost extension, so that total duration was 3 years. And then the leading institute, it was Tarleton State University, including myself and 3 other co-PIs. And also the collaborating institution was Texas A&M AgriLife Research, including Dr. Muir and Brady and other students. So goal of this project is to enhance environmental sustainability on the cattle dairy system using biochar technology. So I list 5 specific objectives in this project. And first one is production of dairy manure and waste hay dry biochar from dairy farm. And then the second objective is biochar application for recovery of nutrient from dairy wastewater. And third objective was to use biochar for removal of antibiotics and removal of pathogen from dairy wastewater. And then another objective is to see effect of different biochar on plant growth, soil fertility, and microbial community. And the last one is to see the economic assessment of biochar technology at dairy farm. So in this talk, I will mostly cover the production of dairy manure and hay biochar up to biochar application for nutrient and antibiotics, and then effect of biochar on plant growth, soil fertility, and microbiome community will be explained by Dr. Muir and Dr. Brady following my talk. So in this project, basically this figure explain whole operating philosophy of this project. So as you can see, dairy farm basically generate huge amount of dairy manure and then also wastewater. And then also somehow the some of the hay becomes actually rotten, discarded hay, which can be recycled for biochar. So as you can see, we basically separate wet manure into dairy wastewater, and then also solid types of manure. And then dairy wastewater goes to lagoon system, where the bacteria degrade the lagoon in the lagoon system to convert to some biogas and also nutrient-rich effluent. And then the solid manure is converted to biochar. Also, in this proposal, I suggest the conversion of discarded hay into biochar, which is actually different property of biochar compared to dairy manure biochar. And then the biochar is used for removal of the contaminant and pathogen from the wastewater from lagoon system, so that the effluent can be more safely irrigated and reused for agriculture. Also, some of biochar is saturated with phosphorus fertilizer, and then we can use phosphorus saturated biochar as a whole biofertilizer for commercial potting mix. So this slide shows what kind of biochar were produced from this proposal project. And actually, I used a dairy manure and discarded hay, mostly alfalfa and Bermuda grass. Also, I used sewage sludge from local water utility. And these three wastes were converted to biochar at 300 to 600 degrees Celsius for half hour to 2 hour reaction time. And then we made into pristine biochar. So as you can see, those pristine biochar has black formable charcoal and some of the porous on the surface. And this pristine biochar surface area is about 10 to 50, sometimes up to 100 square meter per gram, which is not really large surface area, but still it could be useful for several applications. And carbon content of those biochar is 50 to 60%. And then once we apply those pristine biochar for tetracycline and SMX, these are antibiotics adsorption, and then we achieve some of the performance. But those surface area and the carbon content of pristine biochar are not really enough for commercialization of the wastewater treatment. So that I made another process is activation. This means I convert pristine biochar into high surface area porous activated biochar, which is similar to commercial activated carbon. I use the sodium hydroxide or iron ferric chloride as an activator. Those chemicals added to the biochar and then at 800 degrees Celsius for 2 hours. This condition made really high surface and high porous carbon material, which is activated biochar. So that as you can see, surface area of pristine biochar only limit to 50 square meter per gram, but activated biochar has 900 to 1800 square meter per gram. It means huge enhancement of a surface area. Also, carbon content is also increased about up to 82%, which is very high carbon content. So that those activated biochar made high adsorption of contaminant. So you can compare pristine biochar to activated biochar. activated biochar has high enhancement of the contaminant removal in wastewater. Very interesting is those activated biochar surface area and performance is actually better than commercial activated carbon. So F400 is the commercial activated carbon provided by carbon, which is major band of activated carbon in the United States. This F400 has a high surface area and high carbon content, and then also high adsorption capacity. But compared to our activated biochar, it was comparable, or even the activated biochar has higher performance than commercial activated carbon. So that is possible application for water treatment using activated biochar made from hay or dairy manure. And this presentation, I don't really show whole detailed data, but I like to pick up several the data to give you some sense of those technology. So one of them is the application of activated biochar for removal of antibiotics from wastewater. So in this case, target antibiotics is tetracycline. Tetracycline is the antibiotics used for human and livestock application, especially dairy industry used quite some tetracycline for raising cow. So we add 0.01 gram biochar, very small amount of this biochar, put it into tetracycline solution, and then it show actually compared to low biochar and activated biochar show huge enhancement of adsorption of tetracycline. Compared to alfalfa low biochar, activated alfalfa biochar show also very high removal efficiency. And then those efficiency of activated biochar even higher than actually commercial activated carbon. So again, it indicates quite some practical application of activated biochar for commercial water treatment. And another thing is we invest quite some chemical and temperature to make activated biochar, but it's not really economical if we use activated biochar one time and dispose to the land. So more economical way is to regenerate activated biochar and then reuse them for multiple application. So one way is once the activated biochar saturate with tetracycline, and then there's no more adsorption of tetracycline. At this moment, we add very dilute sodium hydroxide and then remove tetracycline so that biochar becomes more free and clean biochar. That is what we call chemical regeneration. So using this process, adsorption and regeneration and readsorption. So we made a 5 cycle, and then very surprisingly, we maintain above 90% of adsorption capacity compared to initial capacity. This means for the multiple application, still we can use same biochar over and over for removal of antibiotics. And another interesting is I made surface modified biochar to recover nutrient, especially phosphorus fertilizer from dairy effluent. So one of them is actually biochar plus calcium compound, calcium chloride or calcium hydroxide, and then make a biochar. So the biochar surrounded by calcium hydroxide or calcium oxide. And then in the wastewater, those calcium species has a high interaction with phosphate. It means actually we put biochar, calcium biochar into dairy effluent. This biochar quickly recover phosphorus to make a phosphorus saturated biochar. And then we can use phosphorus saturated biochar as a whole biofertilizer for soil amendment. So this is interesting data. Low biochar means there's no calcium, and this low biochar show very poor recovery of phosphorus. But once we make a calcium biochar, it show much higher recovery of phosphorus. This means very good technology to recover phosphorus fertilizer from dairy effluent. So looking at this technology, we can recover 80 to 90% of phosphorus from dairy effluent. So that think about, we have about 9 million dairy cow in the whole United States. And this 9 million dairy cow generate about 1.9 billion ton of dairy effluent per year. It contains huge amount of phosphorus fertilizer. So that if we recycle 80 to 90% of phosphorus, it can reward about $35 million fertilizer per year from those technology. So that it is actually high potential to recover phosphorus fertilizer from the wastewater. And actually, in terms of the absorption isotherm, this means we want to calculate and predict maximum recovery of phosphorus using biochar, using some mathematical model. So we have we test biochar to different range of phosphorus concentration, and then we apply 3 different models and friendly Muir tanking model, and those models fit to those data, and then it show the friendly model show best to fit to the data. It means the mechanism wise, this phosphorus removal onto biochar is more likely multi-layer adsorption. This means phosphorus molecule cover onto biochar, and then another phosphorus molecule attach on phosphorus, so that those multiple stack adsorption really make high removal of phosphorus. Also, this data fit to tanking isotherm model. It means the major mechanism is chemisorption. The reason is because, as I show here, main mechanism is actually calcium species and phosphorus. There is a chemical reaction, so that basic mechanism is not physical adsorption, is more likely chemical adsorption. So that this model indicate actually in the broad range of a condition, calcium biochar have a higher capacity to remove phosphorus from the wastewater. And also, I apply calcium biochar for actual dairy effluent. And the dairy effluent contain high COD, about 1000 ppm, also high phosphorus, about 30 ppm, and then other impurity. So basically, usually when we apply biochar to wastewater, other impurity really interfere the adsorption of a target contaminant, so that the performance of biochar in dairy wastewater should be lower than performance in DI water. But surprisingly, the performance of calcium biochar in dairy effluent was not really lower than actually DI water. It means the calcium biochar has a very, very high selectivity to remove phosphorus compared to other contaminants. So this data show we just add 1 gram to 10 gram biochar per 1 liter of dairy effluent. Basically, 10 gram per biochar remove about 95–96% of phosphorus, and then still 80% COD. So that one thing is high recovery of phosphorus. The other thing is high removal COD means high removal of organic contaminant from the dairy effluent. So this slide show what are the possible application of biochar to remove phosphorus and then apply for field. So if we use only calcium,
Dr. Khan,
yeah.
are we allowed to ask questions during the presentations?
Of course.
Okay. Did you see any differences in nitrogen components as well as potassium with the different biochars, especially the calcium?
Yeah, so the answer is the calcium biochar show high removal of phosphorus, but not much removal of nitrogen and potassium. But the magnesium biochar show better performance of the the phosphorus and ammonium. So
Okay, but so could you use other cations that might be and/or anions that might capture nitrogen
yeah,
and or potassium? And if you can, could you mix those three derivatives? Like, so let's say it's something else than calcium that works for nitrogen or potassium.
yeah, of course. So I think I didn't really make the hybrid biochar in this proposal, but from other side, we can make actually calcium magnesium biochar. This means we can add calcium and magnesium onto biochar to make a calcium magnesium biochar, and then this calcium magnesium biochar can remove both phosphorus and ammonium and some potassium. So we don't have to use multiple biochar. We can make one biochar having two or three different sites, calcium, magnesium, remove multiple nutrients.
Okay, I guess the point I'm trying to get to is there's a lot of the wastewater facilities around for dairy and for all types of CAFOs. Could this be used to create fertilizer that's NPNK?
Yeah, it is possible. Yeah, it is possible. So there is a multiple metal attached biochar, as I said, calcium magnesium biochar, and then we have another process is sturobite. This means we set to alkaline pH and calcium magnesium biochar and nutrient all turning into powder and settle
Okay.
down. That is actually two-stage process, and I think that's the one of the ideal way to recover multiple nutrient and then turning into powder.
But that's enough for now. I did have a wastewater company call me about, I don't know, before the end of last year, and I want to call them back with you and talk about this, but I need you to get your disclosure in first.
Yeah. So I guess disclosure. Okay. So that's why in this slide, two-stage is really recommended. The first, we use pristine biochar. We remove organic contaminant first. And then, because a lot of dairy wastewater and wastewater contain organic contaminant, first we remove using pristine biochar, and then the leftover the wastewater contain more likely inorganic nutrient. And then this time we can use calcium biochar more efficiently remove phosphorus and other fertilizer. So that final product is actually fertilizer saturate calcium biochar. And then we can apply to field. That's actually the whole concept of this process. All right. So thank you for your, thank you for your comment, Dr. McCutcheon, and I'll move on. Another one is actually ion activated biochar for removal of contaminants, especially antibiotics and further into PFAS. That is actually one of the ambitious goals from this project to the next project. And one of the things is we have a waste hay, the Bermuda grass, and then we add the ferric chloride. And then we have a one step, 800 degrees Celsius and 2 hours. We made a really high surface activated biochar surrounded by iron oxide. And this is actually very unique types of biochar because the iron oxide show the magnetic property, so that we put this biochar into wastewater, and then we recover of this biochar using the magnetic property. So as you can see, after using this biochar into wastewater, on using simple magnet, we can separate biochar. That's the wonderful beauty. And this biochar has a very high surface area. It means very high absorption of organic contaminant. More importantly, those iron oxide is a catalyst, so that we can actually make a chemical oxidation to degrade antibiotics and PFAS and algal toxin using this technology. So the mechanism wise, the first, this biochar, iron biochar has high peak of magnetite and other iron oxide. Those are very good evidence of iron catalyst to degrade contaminant from the biochar. And then in terms of mechanism, if we have, this is actually SM antibiotics. If we have an antibiotic in water, then first they attach on the biochar. And then we inject some amount of H2O2. The H2O2 contact iron oxide to generate radical. This radical oxidize SMX into water and CO2. So using adsorption and oxidation mechanism, we can continuously actually degrade antibiotics in water. And then biochar can be used for multiple and long-term period. And I test with different H2O2 because H2O2 chemical is the major source of cost. So which I try to minimize cost of this chemical, and then it end up only 200 ppm H2O2 is really provide good antibiotics oxidation, so that it has some other potential for economical water treatment. And another interesting topic is I use biochar to remove E. coli pathogen from stormwater. So stormwater has a lot of contaminants, especially E. coli is a major contaminant. So we have to remove E. coli from stormwater before release to our environmental system. So in our case, first I made a synthetic stormwater, and then I inject intentionally E. coli up to 100 CPU per milliliter. And then I add 5% biochar, which is quite a small amount of biochar. And then this is a very interesting one. When I use only sand column, is a very small amount of E. coli is removed. But when I add pristine biochar, it was 80%. When I add iron activated or NaOH activated biochar, it shows almost 100% removal of E. coli. This means using this biochar, we can remove completely E. coli from the stormwater to provide clean water to the river and then groundwater. And the mechanism is very interesting. Number one is the E. coli can be attached on biochar or can be squeezed between the sand and biochar. So one is adsorption, one is strain, physical trapping. So to make high removal of E. coli from the wastewater using biochar, we should have three important properties. The biochar should have a high surface area and carbon content. And then biochar should have a high hydrophobicity to remove E. coli onto biochar. And then biochar better have a high roughness. High roughness means high active site to remove E. coli. So based on these three ideal property, one of biochar, which is NaOH active biochar, show best removal of E. coli from stormwater. And this is actually, I took the agricultural runoff water from our Stephenville microplot site. So Dr. Muir actually managed the dairy manure applied microplot at Stephenville. And one of the site, we took the runoff water, it containing a lot of actually E. coli and phosphorus, ammonium, and COD. So I apply the different biochar to remove E. coli from the agricultural runoff water. So there are interesting data. When you see the total E. coli, using the iron and NaOH activated biochar, remove 95% E. coli. This is outstanding. And then also, the biochar show quite some.
Dr. Khan,
Yeah.
when did you confirm this?
When did I confirm?
Yeah.
Conduct this test?
Yeah.
Yeah. This one is I conducted this test, I think last summer or early fall. Well, we took the runoff photo from our site.
Okay.
All
right.
This is Jeff at the Temple Center. One question on this slide.
Okay.
So do you remember the baseline E. coli CFU per 100 mil value?
I have a value. Yeah, I didn't put this slide, but I have all condition, real condition.
I mean, just kind of like hundreds or thousands. Do you have a number?
I don't remember exact number, but there are some numbers. So this is only show removal efficiency, but I have an absolute number of E. coli from the runoff water.
Yeah, I'm interested in kind of learning how much was there in the baseline plot.
Yeah. I think so. I don't remember exactly, but range is several hundred. I think several hundred to, I think so, several hundred up to several hundred CFU for the ml might be the range. So you can consider. I will actually provide more exact number of E. coli. Okay, from the user.
So you looked at. I'm
Yeah.
sorry, I don't want to get us off track,
No,
but you looked at colony forming units.
Yeah, CFU.
Okay. All right.
Yeah. So I think that the major message is the NaOH and ion activated biochar having high surface area can remove E. coli at the high rate. I think there's a major message. Another message is also those biochar can remove actually some other nutrient and COD. So in other words, in the presence of multiple contaminants, still this biochar can remove E. coli. That's the message from this one. Okay, and then last objective is effect of biochar on plant growth, soil fertility, and microbial community in the greenhouse test. So in this project, Dr. Jim Muir and Dr. Jeff Brady will conduct greenhouse test in terms of plant growth, soil fertility, and microbiome. And they will present actual data in following my talk. So I don't really present the data, but I just briefly explain. In the greenhouse test, we have a sandy loam and clay, and we have a different biochar, dairy manure, wood biochar, or manure wood blended biochar. And then also the biochar saturated with dairy wastewater or unsaturated. So we can see effect of saturation of biochar with dairy effluent. And then for plant, for warm season is Bermuda grass cowpea. And of course, Dr. Muir and Dr. Brady's lab analyze plant dry weight, plant nutrient, plant antibiotics, and soil nutrient and mineral. And my lab analyze soil antibiotics, pathogen, exo. Also, Dr. Brady's lab analyze soil microbiome. And this is actually the move to another project. So second project is the USDA-CIG grant. And then the Texas A&M AgriLife leading this project, and Extension and Tarleton State University, Texas Tech are helping as a collaborator. And this project is basically biocarbon enhanced dairy manure management for enhancing water quality. Especially, we target to lower phosphorus content in runoff water. So that basic goal is we develop specific biochar. In this case, calcium modified biochar for the removal of nutrient from soil and water, and also the agronomic benefit. It means to enhance plant growth and soil fertility. And of course, we set up the biochar, amended the manure applied field, and also we test biochar for different multiple compound in soil and runoff water. So I don't want to really explain a lot, just briefly one slide before going to Dr. Muir's talk. And we made basically different microplot with different soil, sandy, loam, and sandy, and different plant, forage, grain, energy crop. And we have a biochar, wood biochar, and calcium biochar. And we analyze plant growth, soil nutrient, antibiotics, and pathogen. We also have a macro plot, and here, and there is actually the different system. This is from Temple project, but plot 1, 2, 3, 4 has a different plot for runoff plot. So in this case, we monitor water quality from runoff plot. And maybe Dr. Muir will present about plant growth, composition, and soil nutrient under different conditions. And we start to field 2021, and last year, and this year, it will be a third year demonstration. And then Dr. Muir's lab have been analyzing soil and forage sample for nutrient. And same as Dr. Muir, Dr. Brady's lab also analyzing microbiome component from the soil and forage, starting from 2021 until right now, it becomes third year. And I like to just show the couple of data to compare nutrient in runoff water using different plot. So we have a runoff water plot, 1, 2, 3 is, 1 is a no-till and no biochar and manure. 2 is no-till and biochar and manure. 3 is tilled, no biochar and manure. And then this is actually a couple of data from the runoff water show actually the plot having biochar show lower total nitrogen compared to other plot without biochar. So that there could be a lot of biochar to reduce nitrogen in the runoff water. Same thing, the phosphorus, it was a slightly lower phosphorus concentration in runoff water from the biochar plot compared to other plot without biochar. So this runoff water will be tested more and more under different conditions and then correlate with soil composition and biochar condition to see the more exact mechanism of biochar for the water quality. Another interesting is I also measured Ecology from runoff water from manure applied plot. And as you can see, also the plot with biochar show lowest Ecology number compared to other two plot without biochar. So as I show earlier slide, there is a mechanism of biochar to remove Ecology. So I think same mechanism apply to this biochar to remove or reduce Ecology from water quality. So Dr. Muir and Dr. Brady will make a more detailed talk for the plant and microbiome aspect of biotechnology, biochar technology. But after this project, actually, after this talk, but we'll still need to make some correlation among the biochar, soil, plant, and water interaction. And then also the applying biochar for greenhouse gas control is also one of the emerging topic. And then at the end, water, energy, agriculture nexus using biochar concept will be the one we can make a further study. And I like to appreciate the funding agency. One is a capacity building grant from NIFA and also NRCS-CIG grant, also another NRCS grant from Temple Station. So I like to finish my talk, but I welcome any question and suggestion and feedback. Thank you.
Eunsung, this is Edward.
Yeah.
A quick question on the biochar data that you showed with NMP concentrations. I assume you have the flow rates, right, for both?
So which slide you're talking about?
I think it's about 4 slides up, I'm thinking. You show the nitrogen and phosphorus concentrations for the test plots for biochar. No-till, without, and with biochar. Yeah, that one.
Yeah, that one. Yeah.
You do have the flow rates, I assume, right, for these two.
In terms of rate?
Yeah, the flow, I guess you've got the concentrations, right? But I assume you do have the rates as well, the flow rates.
Oh yeah, we have a
Okay.
we have a certain flow rate.
Okay.
So basically, this is actually we have automatic setup for runoff water from the plot, so that
Okay.
we have a certain flow, but basically it indicates actually runoff water quality.
Okay. Okay, I'll reach out to you later.
Yeah.
Thank you.
Yeah, we have actually quite some runoff water data, but also we'll get more data so that we can
Mhm.
make a good correlation.
Okay.
Okay, so if you don't have any specific question, still you can reach out by email, and then I pass to Dr. Jennifer Spencer for the another talk. Okay, thank you very much.
Thank you, Dr. Khan. So next, we're going to have Dr. Jim Muir. He's a Regents professor in Grassland Ecology for Texas A&M AgriLife Research. So Dr. Muir, whenever you're ready, you can go ahead and begin.
It's a pleasure to be here this afternoon. Thank you, Dr. Spencer. I'm going to see if I can share my screen here. Okay. It's taking its sweet time.
Isn't technology so fun?
Yeah, it's asking me what, oh, there we go. Each one of these software packages have a different option. Do you see my shared screen?
Yes, I do.
Right. Is it with the notes or without the notes? Because it didn't allow me to select the screen.
It's with the notes, but that's okay.
Okay. I wish I could switch them around, but yeah, we'll work on this. I don't have any secret notes, so we're good. So thank you for allowing me to talk to you a little bit this afternoon about the agronomic aspects of our research here with biochar. I'm a grassland ecologist at Stephenville with AgriLife Research, and Paul DeLon, my co-author, is a soil ecologist located at Vernon, and he's cooperated with us in this research led by Dr. Khan. And so even though we look at many different other aspects, really the focus that I have, that we have in terms of agronomy, is biochar and manure in different soils. And the overall purpose is to meet growing food demand. So we're looking at forages. And by doing that, hopefully we'll, or to achieve that, we'll use less land to produce more food at lower costs. So that's the overall goal. While we're doing that, we hope to reduce some of the environmental issues or costs that are involved with forage production in our in our region here in North Texas. So I think Dr. Khan did a good job describing what biochar is, but quite often it's used interchangeably with the word organic carbon or adding organic carbon. So it's a way of adding organic carbon to the soil. And again, as Dr. Khan explained, low oxygen content, high temperatures are used to produce it. And then the biochar is extremely stable in the soil, as we'll see as we talk a little bit more about it. So it's a long-term amendment. Unlike manure or compost and so forth, those are shorter-term organic carbon additions or amendments to the soil. Biochar is a long-term one. There are positives, there are negatives. We'll talk a little bit about those. And then if you're a soil scientist, I don't know, maybe Dr. DeLon would disagree with me to equate biochar as an amendment to what we normally consider to be soil humus. But a good example is terra preta, which can be seen in the Amazon. It indicates to me that biochar is not a new idea by any means, by any stretch of the imagination. Agricultural systems in South America, as well as Africa and other parts of the world for that matter, Asia, have been using biochar for millennia, really, if not, or at the very least, centuries, to improve agricultural production. And so Europeans did not invent this, and we're basically reinventing the wheel here in terms of the agronomic aspects. Environmental issues may be more debatable. So it's not the same as composting organic carbon, and so we have to be careful with making the distinction there. And it's definitely not the same as ash. So if you think adding biochar to your garden or your backyard is the same as spreading your barbecue ashes from your barbecue smoker, you're doing very different things. Ash no longer has any carbon after burning because it was burned in the presence of O2, of oxygen, and contains a lot more mineral content. Non-organic mineral content than biochar, so very different. It's also a long-term investment, which is difficult in our day and age. And Dr. Osei will tell us at the end of this project, whether economically we can afford to use it in the short term. It's a long-term approach, and we, as a country, really, and many other countries as well, have not been very good about looking into the future and investing in the future in terms of what will be useful and productive in the land 500 years from now. Biochar the effects can range that far out, and measuring economic returns for or land managers today, 500 years from now is a difficult thing to do, difficult to convince people to do that. So we're going to talk about the agronomic aspects of our research here, focus primarily on the soil and the plants and the results to date, and maybe a little bit about what we hope to achieve in the future.
Dr. Muir?
Yes.
So is Dr. Osei, and are you, this group, you're looking at things beyond just forage economics with the different treatments, biochar? Are you looking at wastewater cleanup, ways to supplement, let's say, row crops or vegetables? That all gets back to return on investment and economies of scale.
Yeah.
Dr. McCutcheon, if you'll give me a chance, I'll explain what we're focused on in this research.
Okay.
Dr. Osei is a team member, and he is the ag economist who will take all of this information and make sense of us, economic sense of it for us, and
Yeah,
land
and
in the
Jim,
future.
and if I'll just make a quick comment. So there are a couple of projects. Yes. So one of them deals primarily with the dairy aspect of it in terms of utilization on dairy farms. And then there's another aspect that goes more regional that looks at the other issues you were mentioning.
Okay.
Yeah.
Yeah, but you're absolutely right, Dr. McCutcheon, that this has applications in the ruminant production industry or dairy industry, but could also affect other aspects as well. So we're talking about, our focus anyway is west of I-35 and within Texas, and that region is, because of its low rainfall, very poor soils, cold winters, hot, dry summers, unpredictable weather. I'm wondering why we're even in Texas after all this list of negatives. It's very tough on row crops. If you don't have irrigation and an exceptionally stable rainfall year, forages and livestock production, ruminant production specifically, are basically your only option. So our team is focused, in answer to Dr. McCutcheon's question, focused exclusively on forages, because this region is simply not appropriate for row crops without irrigation. And so we're talking about dry land management, and we're talking about forages that can be rangeland and cultivated pasture, but primarily cultivated pasture. Our own, the agronomic aspects look at primarily at nutrient cycling. I'm not going to talk about pathogens or antibiotic residues and so forth. So we're looking at the cycling there, and our goal eventually is to have Dr. Jayhawk have a complete model of what happens to our nutrients, our dairy CAFO nutrient cycles in forage systems within our region. And that's the end goal. And we're providing the nutrient aspects of that. The organic carbon is extremely important in soil. If any of you have studied soil science at all, and it has similar role as clay and humus, but or humus, but it's different in the sense that potentially it could release those nutrients, or even if Dr. Khan has anything to say about it, provide nutrients, come loaded already with nutrients, whereas clay and humus, or clay does not. Clay, it holds on to moisture and nutrients. Humus and biochar, I think, can actually provide a slow release type of fertilizer. So there's this slight difference there. Just a little bit of background. Our ecosystems here, our agricultural ecosystems around the world, due to increased population, human population, but here in North America is no exception. We've been pretty hard on our soils, and our organic matter in the soil has gone down over the last, since Europeans colonized Texas. We've been unkind to the soil, unkind to the ecosystem. And so as a result of that, decreases in soil fertility, problems with erosion, surface water quality, and so forth are what our funders and NRCS especially, and USDA in general, are interested in us looking at this biochar issue. The benefits are multiple. I'm not going to get into those in much detail. If you want more detail, there's a previous webinar on this website that Dr. Spencer has put up that looks at those. But biochar has a potential for a wide range of contributions in the ecosystem. It's important, I think, for us to realize, or for you, the listener, to realize that this is sort of a description of most soils, clay, sand, and silt. So all soils that I'm familiar with are 100% these three elements. The more you go to the top, the more clay, to the right, more silt, to the left, more sand. Most of our soils that we're interested in are in this area here, sandy soils. And that, I think, is where biochar can make a difference. If your soil is more in this direction or that direction, biochar probably shouldn't be of much interest to you, and you can quit listening to this webinar right now and go listen to something else. But if you're in this region, if your soils are within this sandier, coarser textured soil, then you're in the right place. It's not all positive. Biochar normally does not bring its own nutrients, so when it gets into the soil, it neutralizes nutrients. It sucks them up. They adhere to the biochar, no longer available to the plant. So it's not all positive, and we have to be very careful about that. And that was one of our goals. One of our hypotheses in general were that adding biochar would decrease soil fertility and soil nutrient availability to forage plants. Especially micronutrients can become an issue for that. And in terms of producers, in terms of land managers, there are issues that need to be looked at. So what's the future in our region? That's what we looked at in our experiments, is what it could provide as a benefit. And our research, we're very much at the research stage. We don't have recommendations at this point, specific recommendations. So I'll put that out there right up front. Please be patient, though, that those results will eventually be out here. But one thing is for certain. In all of these questions that we're asking, biochar definitely plays a role, and a lot of research around the world in forages and row crops, horticulture, even ornamental horticulture, biochar has been very useful, and that's what we're trying to research with forages. Research with biochar has been a lot less widespread than with row crops and horticulture and so forth. So we're looking at this by species, different forage species, by different soil textures, by different tillage methods, i.e. incorporation or not, biochar in combination with manure. And these are the findings we've come up with, is that it does make a difference what species you're talking about. Texture makes a huge difference. Tillage is important. Incorporation into the soil is important. Laying it on the surface and walking away. With manure, the same as with biochar. You're going to be losing most of the benefit of that biochar. And biochar by itself is not going to do the trick. It has to be in conjunction with manure or other sources of nutrients. And so we've looked at relatively high rates of biochar in our studies. And we found that in terms of the forages, and again, in terms of forage yield and forage nutritive value for a ruminant, a cow or a goat or a sheep, biochar doesn't really change or doesn't really affect forage species that much. That's our preliminary results from the first year, and this is just the first year in 500, right? So it doesn't really affect forages that much. If all you're interested in the forage species, biochar is probably not what's important to you. Some of the micronutrients are affected, mostly because they adhere to the biochar, but really not enough to affect ruminant nutrition. So the first research results we have were put together by a graduate student at Tarleton. Cosette has already published this in agronomy. She looked at 3 factors, and it was a greenhouse study. She looked at, and we call it our cool season, the greenhouse study. So she looked at crimson clover and annual ryegrass, both cool season annuals, very familiar to most people here in North Texas. She looked at 3 different types of biochar: the wood, which is a commercial dairy, which was produced by Dr. Kahn's group, and then a mixture of the two. Those 2 biochars are very, very different from each other. Wood is almost 100%, wood biochar is almost 100% carbon. The dairy is, a large portion of it is ash, a lot more nutrients in there. And then with Dr. Kahn's invention or intervention, we had saturation or not with dairy effluent. So we took the biochar, let it soak basically in dairy effluent, and then tested it. The idea being that nutrients from the dairy manure would adhere to the biochar and then be available to the forage crop once it's applied to the field, or at the very least, prevent the biochar from sucking up nutrients in the soils and thereby decreasing forage production. The results, just in general, we looked at several different rates of biochar: 0, 2, 5, and 10%, I believe, in the pots in the greenhouse. By the time you get to 10% biochar, that's a huge amount. It's an unrealistic amount in terms of a field application, but in terms of a greenhouse situation, we could afford to do that. Crimson clover just disappeared. It shriveled up. It could not pull enough nutrients, sufficient nutrients from the soil to survive. So there is a limit to the benefit of, or even the tolerance that some forages will have for biochar. The ryegrass, on the other hand, was much more capable of competing with biochar for nutrients, and so especially with the effluent saturated nutrients. So it did fairly well. So that pretty much summarizes what Cosette found in her greenhouse, cool season greenhouse studies, especially the differences between wood and dairy. Those 2 biochars are very, very different in terms of their effects, negative or positive, on those forages. The dairy being a lot less negative and more positive than the wood by itself. So this gives you a quick overview of what we had to work with. The wood biochar, the manure biochar on the right, and the different nutrients. And this is a percentage here, all these, and then the parts per million down here that are smaller amounts. These are micronutrients. These are, most of these are macronutrients. And so you can see that the manure biochar, for example, the ash was almost 40%, whereas ash in the wood biochar was only about 6%. So ash would be providing such things as phosphorus or potassium. Won't be any nitrogen in there or not. So that's why we were seeing a difference between wood biochar and the manure biochar that Dr. Kahn is producing with manure and discarded hay and other organic materials available at a dairy.
Jim?
Yes, sir.
For us non-agronomist, can you explain the crimson clover? I.e., why was it so impacted?
I cannot explain that. I do not know the reason why. So that's on our list of future research. There are some, we have some theories or some hypotheses. The crimson clover is a broadleaf, dicot. It has a taproot, and the root system is not as thorough at gathering nutrients and moisture from the soil as a grass, which is what the ryegrass was. The ryegrass has a much more fibrous root system that spreads out into the soil and can compete. And legumes, as well as grasses for that matter, but legumes especially, are very dependent on the soil microbiome to help them overcome the lack of an extensive root system. The advantage of crimson clover is that it can go deep into the soil, much deeper than the grass. But the grass has the advantage because it can be much more efficient at capturing nutrients and moisture in the soil surface. Yes.
A couple of more questions. Very interesting. Did you see any other dicots that we would call weeds? Emergent or smaller weeds, were they depleted?
This is a greenhouse study. So if you'd had other species, I would have been all over the graduate student for not weeding her pots. So no, we did not. But that is a very good question, obviously.
Right.
Because, when we moved with this to the field, and again, I don't think because if you look down here on this table, the loading percentage to 0%, 2, 5, and 10%. Dr. McCutcheon, I don't think we need Dr. Osei to tell us that 10% is never going to be economically efficient.
Right.
It's just the land managers will never be able to afford that. But it's at that 5 and even 5%. But that 5 and 10% is where, as you can see on these rows, the crimson clover just gave up. It was starving to death. I think if we put some of Dr. Brady's endophytes in there in those pots in the greenhouse with these, the crimson clover, I bet you anything they'll be able to overcome.
Yeah. I just it's something to keep in mind as we go to the field on how we might have different treatments, looking at different the amount of broadleaves. Do you know what impact that would have on the overall forage for ruminants?
I'm not sure I understand your question. You're talking about the weeds or the legume?
The legume.
Well, obviously, if you have 0% production, you're going to have starving cattle. So I can predict that ruminant production will go down in that situation.
Okay.
But the nuances come, with saturation or not saturation,
Right.
And with the different, types of biochar. And so this study, and there's a second manuscript coming out looking at the microbiome. And I don't know if Dr. Brady is going to talk about that or not, but from this exact same trial, there's going to be some a second publication there looking at that. So I'm personally very curious to see what's going to come of it.
Yeah, I'm very curious. This is exciting. So anyway, I'll save the rest of my questions.
Okay. This is the previous one was on above ground forage production. This is on root dry weight, and the correlation here being zinc. We're looking specifically, she looked at zinc, and as zinc went up, root dry weight went down. And so who knew that zinc could be toxic? And she found a whole, Cosette Taggart found a whole series of research publications indicating that too much zinc is a bad thing for forages. So we confirmed that with the biochar. And so there was a second trial, greenhouse trial, warm season. Again, 3 factors. The forage species, of course, were warm season, Bermuda grass and cowpea. Biochar, same difference. And then the saturation and no saturation, also the same treatment. That one has not been analyzed yet. We finished that last summer, and we're still looking at the data. And so keep tuned. We'll let you know if, for example, that whole, because cowpea would be the equivalent to the crimson clover, so the taproot, Dr. McCutcheon, and Bermuda grass would be, equivalent to the ryegrass, the fibrous root. So I'm dying to find out whether, we have the same situation in which the biochar is not as beneficial to the legume as it is to the grass, but those results are still on the way. We also have field trials, and as Dr. Khan explained, these field trials encompass a couple of different grants. This particular one is a little bit complex. I don't know who designed it. That's a 5-factorial experiment with rates of biochar. That's megagrams is the same as metric tons per hectare. If you're more into the ye old English units, you can look over here. With or without dairy manure. So we didn't use saturation. We just used manure. And that again is at 10 tons per hectare. That's not a very excessive rate.
How did you prepare the manure and the biochar?
The biochar in this case was purchased. It was commercial wood biochar because the quantities were it was beyond the scope of Dr. Khan's group to produce. The dairy manure we collected at the Southwest Dairy, and it came from their flush system. So it was low in nutrients but high in organic matter, and we basically collected the floating part, the organic part, and dried it out, and then applied it on a dry matter basis. So 10 tons. So ended up being about 50 tons of wet weight.
Yeah. So how did you? What was the idea behind the mixture of the biochar with the manure?
Well, in some cases we did not mix it. So
yeah,
there's some biochar treatments here with 0, and some dairy manure with no manure. And so we're comparing the two. And I'll get to the preliminary results in a second here. But you're onto something, Dr. McCutcheon, in that the combination of the biochar, just to give a little hint of what's to come, combination of biochar and manure had the most effective, the greatest effect on soil. So we had 3 different types of soil at 3 different locations. As I pointed out in that little triangle, some had more clay than others. We also had tillage or no tillage, so applying it to the surface or not. And then we had 3, and still have, because this trial is continuing. It'll continue on for another 5 to 500 years, depending on the funding we get from NRCS. And Miss Hayes is about to defend her thesis next week on Monday. If you're interested in seeing the results in detail, you'd be very welcome to. She's going to be defending it right here at AgriLife at what time? I can provide that information if you'll email me. So in general, I read her thesis, and in general, biochar does change nutrient availability in low clay soils or high sand soils. and it generally changes CEC and pH. But not so much the nutrients. So, and we're talking about plant available nutrients, so malic 3 type nutrients. There's a second graduate student, Mr. Cooper, who is looking at the forage aspects of the trial. Just to summarize very quickly, he hasn't written his thesis yet, so I don't have as much information on the forage side of things, but forage yield and nutritive value was basically unaffected by biochar manure. Now, I probably didn't explain to you earlier that the manure plots received as many nutrients as the non-manure plots. So there's no surprise here that yields were not different from manured to unmanured plots and biochar to unbiocharred plots, because we applied commercial industrial fertilizer at the same NPK rates to the control plots as we did to the manure and biochar plots. But the bottom line is biochar did not change forage yield or nutritive values. There were some slight decreases in iron and magnesium, but when Mr. Cooper looked at the nutrient tables, for a dairy cow, for example, he found that the decreases that we saw in the forage levels, in iron and magnesium, would not affect a dairy cow. So basically, he was disappointed that there was no effect of biochar or manure on forage yield or quality. And we're talking 3 different species here, very, very different species, because the corn is a silage, one harvest system. Sorghum Sudan is a hay system, harvested 2 or 3 times in a season and then dies off. And then the Jigs Bermuda grass is a perennial system that'll go on for 30 years if properly treated. So it comes back every year. And so all 3 of those have basically the same response. We don't care if we have biochar or manure in our plots or not. We're going to do just fine if you provide us with inorganic fertilizer, NPK at the appropriate amounts. He was disappointed, like I said, but as far as I'm concerned, I wasn't really disappointed, because this tells me that if you need to apply biochar for the long-term effect, or for decreasing the long-term costs of inputs like inorganic fertilizer, or for mitigating pathogen infections in the soil, or for destroying antibiotic residues in the soil, then you can do so without negatively affecting the forage. Because recall from earlier in our talk that one of the issues with biochar is that quite often it has a initial negative effect on crop production. And we found that this was not the case as long as everything was fertilized adequately. Just a quick result from Hayes research on the soil, because once again we're looking at electrical conductivity of the soil, and we had a soil by tillage, by biochar, by manure interaction, one of those nightmare interactions from an agronomist point of view. Biostatisticians, we're very happy to see it. I'm sure they get all excited about those things, but when it comes to biological explanations for these interactions, they become a little challenging. But what's interesting here is, I'll just pick out this quick thing, and then we'll end our talk here. But here is the tillage systems: no till, till, no till, till. Here's the manure added, manure not added, and here's the no biochar, low biochar, and high biochar. So we're looking at high biochar with manure, no tilled and tilled. So no tilled and tilled. And that's where the big difference occurred. If you have high biochar and manure added, and did not till, then the benefits of the combined benefits of biochar and manure were negligent, were negligible. So there were no effects or even negative effects if you applied it to the surface compared to when you tilled it. It's when you tilled it in that you got a benefit in terms of electrical conductivity, which is a measure of how soil particles, or soil can hold nutrients for future use by the crop. So again, the combination of tillage and biochar with manure is where we got the benefit. So a little tidbit there that we're pulling out. So future research directions, keep in mind that the results we have are from the first year out of 500 years that we're going to be running this trial here at Stephenville. And so medium and maybe long-term results are a bit ambitious, but medium-term results would be good in terms of these interactions. We need to look beyond the short term to the medium term. We also need to figure out exactly how much biochar is good and how much is bad. That has to be the next focus. If we don't know how much biochar to recommend to land managers in the area, we're not going to have done our job here at the end of this project. And then, which one of Dr. Khan's biochars is the best? Which material? How to saturate it or not? How to manipulate the soil? Whether to till it or not till. I think we're answering that question already. And again, application rates, especially of manure and so forth, are a good thing to look at in the future. So if you have any questions for Dr. Lalonde or myself, here are emails.
Very nice.
Yes, it's some very interesting, I would call preliminary data, but already useful data, I think, Dr. McCutcheon, and I think we're.
So I have one question for you and Dr. Khan. What do you believe if we had the right biochar mixture, let's say, what would be the economic impact over 10 years? Just guessing. If you did the tillage, in other words, we worked through the best management practices.
I think that may be a Dr. Osei question if you're still on.
Yeah, I'm still on there. I guess I would say it depends on the extent of the benefit and the tillage costs involved.
Yeah, and then you have to add in, the greenhouse gases and the environmental stability. And I don't know how to do that. So
maybe Jayhawk will help us model that. So we'll have the numbers.
Yeah.
Well, I think those are the types of data that, a lot of government agencies as well as industry and corporations are looking for right now. So thanks for the hard work and the students. And I mean, that Dr. Khan and Muir, and I want to hear Dr. Brady's, but this is excellent.
So that's Dr. Spencer. Sorry, I didn't say that, but that completed my contribution. Thank you for the opportunity.
Yes, thank you. Really appreciate it. So our last presenter is going to be Dr. Jeff Brady. He is an assistant professor with Texas A&M AgriLife Research. So Dr. Brady, whenever you're ready.
Okay, thank you. Good afternoon. Let's see, it's 4:30. Probably a lot of people have a hard 5 o'clock departure, and I don't think I'm going to go that long. Go ahead and share my screen. Okay, can everyone see my first slide?
Yep.
Okay. So I'm Jeff Brady. I'm at the Stephenville, Texas A&M AgriLife Research Center. I'm in the Department of Soil and Crop Sciences, as is Dr. Muir, who just preceded me. My talk is going to be on impacts of biochar on soil microbiology. And so why am I concerned with microbes? Why should you be concerned with microbes? If you apply dairy manure to a forage plot, there's lots of nitrogen and phosphorus in that. Will the plants just take it up, use it as a fertilizer? Yes, they will, but there's another step in there. Microbes also need nitrogen and phosphorus, and they are intimately connected with nitrogen, phosphorus, and carbon cycles. So they're an important key component that producers may not always think about. I'm interested in, mitigating environmental impacts of concentrated animal feeding operations, which includes, pathogens introduced into the environment, as well as the nutrients. So nutrients can cause eutrophication of waterways, and we want to really stop or lose as little of the nitrogen and phosphorus as is possible, because those are valuable nutrients for plant production. And then carbon is a kind of an emerging topic. Carbon sequestration is highly funded at the moment and highly encouraged, and carbon markets are popping up. And so this is kind of the beginning of a new component to agricultural production, and everyone's kind of in the process of figuring that out. Along with the pathogens, sometimes antibiotic resistance genes, antibiotic resistant bacteria, and antibiotics come along in that mix. And we want to keep those out of the environment so that we're not creating cycles of antibiotic resistance that can work their way back to the cattle or back to humans. There are instances of, animal workers becoming infected with an animal with antibiotic resistance, these so-called superbugs, and we want to minimize that. We have new tools to study microbiomes, and that's why I can do this. So just 15 years ago, we really couldn't do these type of studies. If you were trying to study microbiomes and we're using culture-based methods, there's only about 1% of the microbes that exist in nature that you can culture in the laboratory. It's hard to study something that you can't culture. So development of high throughput DNA sequencing methods really was a game changer for studying microbiomes and microbial ecology. We first pointed that new tool at ourselves, and the Human Microbiome Project developed a whole bunch of the tools that we need to study, environmental microbes. So at the bottom here, a DNA sequencing workflow of what do I do and how do I do it? We collect biological samples. In this case, they're going to be soil or plant or water samples that go along with these research plots we have in our biochar studies. And we extract DNA from them. Depending on what we're doing, sometimes we might extract RNA. And then we sequence that DNA, either all of the DNA in that sample, or we amplify a specific target in that sample and use that specific target to study the whole metagenome or everything that's in that sample. And then at that point, it's a description of what is there, and it breaks down into some bioinformatics where you can do some cool comparisons. Kind of visual of what I was just saying. Collect a sample. I'm showing a cannulated cow over here in the top left. Extract and cut up the DNA, and then we put adapters on the DNA. And the target DNA in this case is this light blue, and then that we put a unique DNA barcode on it so that we know which sample it came from. We do this in a high throughput format. So we have a 96 well plate, and each well in that 96 well plate has a sample. Every well has a unique barcode. So this barcode for each well is unique. And we put all of the samples in that multi-well plate together into a single tube, and then we sequence them on one of these high throughput sequencers. And all a DNA sequencer does is generate DNA sequence. It generates 4 bases, A, C, G, or T. And this is a little snippet of what DNA sequence looks like. And we look for differences within those sequences that lead on to doing bioinformatics and community comparisons, where we can tell whether or not a given treatment had an impact relative to controls. And so in this particular, these several studies that we're talking about today, our treatments are biochar. I can do what I'm doing because Texas A&M invested millions of dollars in a genomics and bioinformatics core facility, and I utilize that facility heavily. And anytime I give a presentation, I want to thank A&M for funding that. Dr. Muir mentioned several different studies. This one we call the greenhouse study, the greenhouse trial, cool season greenhouse. This one is what I'm going to talk about mainly today, because it's the one that I have to the most completed step of analysis. We also have the warm season greenhouse study, and we have multiple years now of field study. We use these greenhouse studies to help guide us decide what to do in the field. And in the field, Dr. Muir mentioned that we're conducting a 5 factorial experiment, which creates huge numbers of comparisons that need to be made. And he was saying, who did that? And he was kind of laughing to himself. And me and my bioinformatics postdoc have complained a bit about how many comparisons we're doing, but I think his strategy was an excellent one, and that in the first year or two, we're casting a very wide net and making many tests and collecting lots of data. And then in later years, we're going to narrow it down to really doing in-depth comparisons, probably on the most impactful and important treatments. And as he mentioned, we're at the stage where we can't really make a whole lot of rock solid recommendations yet, but all that is coming. So he's kind of laid out the cool season greenhouse tests, but I'm going to just go over it quickly. There are 3 biochar types: wood, manure, and then a blend of wood and manure biochar. We have 4 different loading percentages: 0%, which would be just a control, and then 2%, 5%, and 10% biochar. And then we have saturated and unsaturated biochars. And these are the biochars Dr. Kahn was describing. He's the kind of mad scientist coming up with the technology that we're using and comparing in the field. And so saturated would be biochar saturated with dairy lagoon effluent, and unsaturated would not have any dairy lagoon effluent added to it. And then different forages, we have a no forage, just bare pot, no plant in it, control, and then cool season plants, crimson clover, and Italian ryegrass. Some of the things I look at are differences in alpha diversity in samples. And the samples I'm going to talk about in this cool season study are all samples that are soil. I don't have any plant samples in this one. But just looking at this top one, the x-axis is number of sequences collected per sample, and the y-axis is observed features. You can think of observed features as bacterial species or bacterial genera. It's at a level somewhere in between species and genera. And so looking at this, if the colors don't show up well on your screen, 0% biochar loading is the least diverse. So as you collect an increasing number of sequences, the curves go up. If it was infinitely diverse, every new sequence would be a new microbe. But eventually you start hitting the same microbe as you continue with higher numbers of sequences. And if you sequence deeply enough, you hit a point of saturation where the curve levels off and you've surveyed almost all of the major microbes present in a sample. And so these curves are leveling off. We probably are fine at this level of sequence depth to make comparisons between the samples. And this is a kind of concentration dependent increase in, so I say alpha diversity here. This is actually species richness that I'm showing, but true alpha diversity is also increasing in these samples. So if you measure Shannon diversity, that is also increasing in these samples with increasing loading percentage. And it is, as I said, concentration dependent. 2% is more diverse than 0%, 5% more than 2%, and 10%
Dr. Brady,
most diverse of all. Yes, sir.
can you explain that in Texan terms?
So you want more diversity. Diversity is a good thing. The more microbes you have, the more functional capacity the soil has. It can break down more substrates, and it's more robust to changes in environment and weather or flooding or extremes of conditions. So more microbes is equivalent to more functional diversity. And so you want, it's kind of like with, the way the world's moving. We want input from more people if we have a project, so that all the stakeholders are represented, rather than just having a few people determine what should be done. We reach out to stakeholders and as diverse as possible and try to get as much input as possible. So for soil functionality, the more microbes that are there, the more that soil can handle.
Okay.
So we want more microbial diversity. And then
Except for pathogens.
so pathogens are going to be there no matter what.
Right.
That is one benefit of high microbial diversity. It stops pathogens from getting out of balance with the rest of the system. So
Exactly.
when you have
I
illness,
think that's, I think NRCS wants us, I know they want a couple of 2-pagers, and what you gentlemen have presented today, both on lowering E. coli numbers with the activated biochar, as well as your findings here. Have you looked at E. coli pathogens specifically in these data sets yet?
I have not. I'm behind Dr. Khan on that. So I'm following up on samples that he's measured E. coli, and I'm confirming with DNA, and he used culture-based methods. So we're using 2 different methods to confirm the same thing.
Right.
But I've not got the data yet.
Yes, of course, soil health is the biggest thing, and having stability over a longer period of time. But also, they want to know, and we want to know what we're doing to potentially, pathogens. E. coli is the big one. You know that.
Absolutely.
Okay, so we're looking at pros and cons, but they can mean something entirely different.
Sure. And
Okay.
one of the measures of soil health is, soil microbial diversity. Higher diversity equals, increased soil health. So that's one
Okay.
of the measures.
Well,
And
we
so,
just need to get this on a couple of 2-pagers. I'm very impressed.
and then kind of similar to the agronomic results Jim was mentioning, wood's kind of similar. It had lower increase of diversity compared to the manure, which is highest in the blend, which was very close to straight up manure biochar and increasing soil microbial diversity. Then we do things like look at just the composition of microbes, and these are prokaryotic microbes, which are basically the ones I've got listed are all bacteria. Looking at this, we have control on the left 2 panels and crop, which would be both cool season plants that were in the pots on the right two panels. And we have no and yes off here on the far right. That's whether or not there was saturation, that lagoon effluent saturation. And then on the bottom, we have the samples and the biochar addition to them. And you can see there's a stepwise increase in many of these samples from 0% to 10%. And this is blend first. The same thing happens in manure biochar, less so in wood. And these are for controls. And then the crop plants, there's also this kind of stepwise increase in some groups. And what we saw is an increase in the purple group, which is proteobacteria, and then a decrease in the kind of light blue group that's up at the top, which is acidobacteria. And this is, due to many factors, but one of the most basic ones is pH. As more biochar increases soil pH, and so acidophilic bacteria like acidobacteria would decrease in number, and bacteria that could tolerate higher pH would expand. And I'll get into some more nuanced evaluation of what happened as we move on. Okay, we can look at gene content for these tests, and this is again the cool season biochar. Looking at the legend over here at the very top line, we got a red, brown, and a darker brown band, and that is blend biochar, manure biochar, and wood biochar on that top line. And then loading percent just below that, gray is 0, this pink color is 2%, orangish is 5%, and black is 10%. And then we have a heat map below that of different genes that were either increased or decreased according to these treatments. If they were increased, they're red in color. If they're decreased, they're green in color. And ones that didn't change much are kind of black. And so you can see groups of genes like this red grouping right here under this manure 10% biochar that were highly enriched in those samples. And then below that are a bunch of genes. And these are just the 50 most significantly different genes picked out of the Italian ryegrass study, just to demonstrate some of the things that we can look at and compare. And I don't want to get into any of these specific ones. I'll get into specific genes in these next slides. This is both crimson clover and Italian ryegrass with the same heat map and same blend manure, and then wood biochars with 0, 2, 5, and 10%. And Dr. Muir had mentioned, that we went beyond the amount of biochar that you would use in the field in this greenhouse study. And we did that so that we could see, some potential negative effects and also potential positive effects. And so one of the potential negative effects we see when we get to, 10% loading, let's see, is this nitric oxide reductase gene is kind of highly enriched in 10% manure biochar. We don't want to enrich that gene because that gene produces nitrous oxide, the greenhouse gas. But back at 5%, there's not much of an impact from that gene. And there's 2 different flavors of that gene up above. So much less impact at 5%, a much more realistic, economic application value. And then the other genes we're looking at, are involved in, we're really concerned with, nitrogen and phosphorus cycling and dairy manure effluents. And so some of the genes we've detected are involved in, dealing with the excess nitrogen and phosphorus that's present in effluents from dairies. So one of the things that I missed, even as a, PhD level plant biologist, because they didn't teach it when I was taking courses, was that, plants aren't the only, plant roots don't only take up these nutrients through like root hairs, like I was taught when I was, in school. And it wasn't that long ago. I mean, it was quite a while ago, but I don't want to date myself, but, less than 20 years ago, we had a whole different view of how plants absorb nutrients. We've learned in the last 10 or so years that plants actually eat microbes at the root tips, and then they strip them of the nutrients and then kick them back out in the soil. So at this root tip, right at the tip of the root, microbes are going to be going in, and as they're going in, the plant is dumping reactive oxygen species on the bacteria and just ripping their cell walls off and sucking the nutrients out of them. So rhizophagy literally means root eating. So the roots are eating the bacteria. As the bacteria travel up the root, this brown staining area indicates where reactive oxygen species is. The stain reacts with reactive oxygen. The microbes travel up the root to the root hairs, where I was taught, absorption of the nutrients occurs. At the root hairs, the plant pushes the microbes out of the tip and pushes them back into the soil as, protoplasts without a cell wall often, and they're kicked back out into the environment with very few nutrients. Some of them survive and some of them don't. The ones that survive, many rhizobacteria have flagella, and they can swim back to the plant root and re-enter the cycle after they've sequestered a bunch more nutrients and are valuable to the plant again. So this is a cycle, and the bacteria can go through it multiple times, and the plant is actually stripping nutrients off of the microbes. So plants do absorb microbes independent of bacteria, and if there's abundant microbes, this rhizophagy process is limited or cut off. But as nutrients begin to become more scarce, the plant starts secreting exudates at its root tip that encourages bacteria to associate with the root zone, and then the plant absorbs it and then sucks all the nutrients out of them and kicks them back out in the soil again. I wanted to point that out because we're talking about nutrient cycling in this project, and it's not just the plants doing that. There's a cooperation between plants and microbes. So, general summary of the cool season greenhouse findings: the biochar amendments from manure, but not wood so much, increased soil microbial diversity in a concentration dependent manner. The biochar amendments with lagoon effluent saturation slightly increased the soil microbial diversity, but not to the same extent that just the plain biochar amendments did. They didn't make that much difference. High nutrients from manure, biochar, and lagoon effluent saturation shifted microbial communities toward R-selected species and away from K-selected species. And so those are broad groups of microbes that are kind of living by a different rule book. It's kind of like the tortoise and the hare. R-selected species grow quickly, sequester nutrients quickly, and turn over quickly, whereas K-selected species are much slower growing and stable in number, have a kind of steady strategy. And what we see when we dump, any manure biochar into our pots was that these R-selected species were increased, which is not surprising. There's a great deal of nitrogen and phosphorus and even zinc, as Dr. Muir mentioned, and we don't want that to pass through the soil and get into the waterways. And so if these, R-selected species can suck up those nutrients, it's really a good thing. If the plants can't handle it all, the plants plus microbes can handle a large amount of the potentially contaminating nutrients. Higher pH of biochar treatments selected against acidophilic microbes, and I pointed out the acidobacteria decreasing and proteobacteria increasing, and biochar binds some of the excess soil nutrients. Soil microbes gather and sequester those excess nutrients until plant roots can then harvest the microbes for nutrition later. So as the soil becomes depleted of nutrients, the plants will switch back to rhizophagy, to eating bacteria. So as long as those nutrients were bound up in a microbe, they're not going to end up in our waterways. And then the warm season greenhouse study, I'm, not nearly as far along on that, but Dr. Muir mentioned a little bit about it, and different soils really have an impact on outcome. If you have a high nutrient clay soil, the biochar amendments don't have nearly as great of impacts as if you're using a sandier soil with lower nutrients. And the plants themselves increase soil microbial diversity relative to amendment application on bare soil. So plants definitely have a role in increasing microbial diversity and recruiting microbes at that root tip. And soil fungi in that particular study were more impacted than soil bacteria by biochar amendment in a concentration dependent manner. And I didn't talk about fungi much, but I'm looking at prokaryotic or bacterial microbes and fungal microbes, which are a little higher order microbial organism. And this is, as Dr. Khan and Dr. Muir mentioned, a group of funded studies from NRCS and non-land grant college and university program through USDA. And one of them is a NRCS conservation and innovation grant. And so there's a large number of cooperators on these multiple projects and lots of moving parts, and all of those people need and deserve recognition. And it is quite a large team, and it's a dynamic team, and I think we're beginning to make some real headway. And I believe that's all I have for today. And it's just before 5.
Awesome. Thank you, Dr. Brady. And I really appreciate you acknowledging all the individuals that have helped out with this. Really quick, I'm going to share my screen. Oops. Not open.
I just stopped mine right as you were saying that. So.
Oh, okay. All right. So I just wanted to briefly explain some of the extension activities that we've done. So we've completed 2 webinars prior to this one. And then we've also had a research showcase that was in person at the Southwest Regional Dairy Center. And then biochar has also been discussed at some of our dairy producer meetings. Developed a fact sheet to hand out to producers, as well as just educate the community. 2 publications have been done for the Texas Dairy Matters articles, which are also published through Texas Association of Dairymen and the Texas Ag and Dairy Review. And we've also given promotional poo emoji stress balls and had educational fact sheets at one of our field days, the Southwest Dairy Day in October of 2022. So these are just some of the results that we got from the 2 previous webinars, and then also the research showcase that was back in 2019 or 2019, yes. And these results are actually submitted for an abstract to the American Dairy Science Association that will be held in June of this year. So with that, if you wouldn't mind taking a brief minute to scan the QR code or copy the link and take that survey, that would be awesome. And if you actually send me a picture of the survey completion page and email it to me, it's still going to remain anonymous to myself at jennifer.spencer@ag.tamu. I will send you a stress ball poo emoji. So with that, thank you so much. And I hope you guys have a great rest of your day.
Thank you.
Thank you, everybody.